Hi, in this video, we'll continue our discussion of proteomics and mass spectrometry. We'll focus on data acquisition. We'll start by talking about peptide ionization methods. This is getting the peptides into the gas phase so they can be analyzed. We'll talk about fragmentation patterns of the peptides, the B and Y ions that are produced. And then we'll talk about the two-step analytic process where we're going to quote-unquote weigh the intact tryptic peptides, and then we'll also weigh tryptic peptide fragments. And this will be the key for interpreting the raw data molecularly, that is, matching spectra with protein identifications. There are two predominant ionization methods in mass spectrometry, and both are depicted here. We'll focus on the electrospray ionization method, as that is the method that's used slightly more frequently. This method is better at handling complex mixtures. The other method, Maldi, we'll discuss here, but we won't say anything more about this method. And this figure is from the review paper which I assigned for reading. And in fact, all the material that relates to Maldi type mass spectrometry has been grayed out. The part that remains focuses almost exclusively on electrospray ionization. Before we describe either of these two methods in greater detail, first I want to point out what a challenging problem this is. Think about a solution of salt water, and if you let all the water evaporate, eventually all the salt molecules are there at the bottom of the glass. Charged species generally don't like to evaporate into the gas phase. Furthermore, these peptides are rather fragile. Methods that are too harsh in terms of vaporizing them will likely destroy them also, and so preclude any real analysis of the peptides. Therefore, the methods were limited for a very long time until these two methods came along for getting peptides effectively in the gas phase. For electrospray, what we have here is we have a very narrow liquid chromatography column. This liquid chromatography column might be 100 microns across. The flow rate might be a few nanoliters per minute. The spray needle might be between 1 and 3 microns, and so a very fine mist is going to be eluding from the column at any particular time. So that's step number one. Second thing is the solution in here is going to be very acidic. There will be lots of extra protons in this solution, so there'll be lots of positive charges. All the peptides will be positively charged, and there'll be a lot of free protons. Thirdly, we're going to put an electric field on the solution, again further increasing the amounts of positive charges that are present in the solution. Now, as this very fine spray, again a few nanoliters per minute, comes out, it's going to start to evaporate. It's so tiny it's going to evaporate rather quickly because it has a large surface area relative to its volume. As the water is gradually evolving, you're getting a large number of positive charges closer and closer to each other. Eventually, you'll have what's called a Coulomb explosion. That is, the positive charges get too tightly compressed into a space, and they will burst the remaining bubble into very fine pieces, almost individual molecules, because of electrostatic repulsion. Frequently here, peptides are associated with maybe a 1 or 2 water molecules, which then will really quickly evaporate in the gas phase in the heated inlet tubes of mass spectrometers. So eventually what you have is a positively charged peptide, naked peptide, in gas phase being directed towards the inside of the mass spectrometer by a negative electric bias, and then it'll be analyzed inside the mass spectrometer. Now the Maldi method, which Maldi stands for Matrix Assisted Laser Desorption Ionization, the laser is going to come in, it's going to blast a matrix molecule, and your peptide ions are the analyte, in this case the analyte molecules, are mixed in with the matrix molecules, so that when a high intensity laser is directed towards the surface, it's going to heat the surface up locally a great deal. You'll get a burst of vapor cloud that contains both matrix molecules and your peptides, which are once again positively charged, and they will be accelerated into the mass spectrometer by an electric field. The last thing I want to say about this slide is that to point out that for proteins at least, there are really only two basic types of mass spectrometry. One is that uses electrospray ionization and one that uses Maldi. Now there are about 100 different acronyms for and variations on these two themes. You might see Maldi-TOF, you might see Celdi-TOF, you might see Maldi-TOF-TOF. Those are all one basic kind of mass spectrometry. The other type of mass spectrometry goes by various names called electrospray, nanospray, tandem mass spectrometry, ion trap mass spectrometry, FT or ICR mass spectrometry. These are all going to be essentially the same type of process. So if you get these two straight, you'll basically understand almost every kind. Now, the way the peptides are detected by the mass spectrometer is a little complicated, but we can get great insight into the process using some very simple arguments. First, we want to say that the way the mass spectrometer is going to measure the peptide is essentially by weighing the peptide very accurately. And there's going to be a two-step process. It's going to weigh an intact peptide that's produced by tryptic digestion of a protein. Remember, trypsin cuts after lysines and arginines. That's going to produce a peptide. We're going to weigh that peptide. The second thing we're going to do is cause the peptide to fragment, and then we're going to weigh the fragment pieces. And by knowing the original peptide weight and the lots of fragment weights, we'll be able to computationally identify what protein must have given rise to that set of signals. Now we can talk about weighing or measuring the mass, but what you're really measuring is the mass to charge ratio, and you'll see this abbreviated as m/z, mass to charge. And from this number, if you happen to know the charge, which you can deduce from the mass spectrum, you can then compute the mass. So if you see a signal at 500 Daltons and you know that that peak is due to a +2 charged particle, then you'll know that the mass of the original peptide is right around 1,000. This consideration of mass to charge ratio was also the same type of considerations in the Millikan oil drop experiment, in which the mass of an electron was deduced. So one of the consequences of measuring m/z is that if z equals 0, you cannot measure the mass. That's one of the reasons only charged peptides are observed in a mass spectrometry experiment. This last paragraph just reiterates the challenge of getting peptides into the gas phase. So let's think about measuring the mass of a charged particle. I want you to think about these large circular atom smashers, in which case you have atoms or other charged subatomic species traveling around at speeds close to the speed of light, and they are all charged, and there are magnetic and electric forces that are going to cause the beams to bend inwards. And for a certain mass traveling at a certain speed, there'll be a certain amount of force that's required at all places in this circle to have a stable orbit. If you have, say, you put 3 particles into the cyclotron, and one of them has a stable orbit, and one of them is lighter than the particle that's stable, that's going to collide to the inside walls, and if one particle is heavier, it will collide with the outside walls. It won't have enough force to continue its circular orbit. So by knowing the amount of force that you're providing to bend the particle into the circular orbit, you can figure out the mass of the charged species. So this is not an exact analogy for what's going on in the mass spectrometer, but there are going to be certain fields that we're going to create inside the mass spectrometer, and only particles of a certain mass will have a stable orbit and proceed through there. Other charged species, whether lighter or heavier, will collect on the walls of the instrument because they won't be able to pass through all the way into the detector. Now here we see a peptide. We have an amino group, an alpha carbon, and a carboxy group. And then here we have an amide bond, an amino group, an alpha carbon, a carboxy group, an amide bond. So wherever you see these, there's a line that's listed as a Y ion, or as a Y line. That's where all the peptide bonds are. Now here's a miraculous thing. If you put this peptide into the gas phase and you put it into a mass spectrometer and you bombard it with atoms of an inert gas such as argon or helium, there's going to be collisions, which is going to impart kinetic energy from the gas to the peptide, and it's going to produce the fragments of the peptide. It's rather remarkable, but the peptides tend to fragment right along the peptide bond, so that if you have an overall peptide, each peptide will on average fragment once. Let's say it fragmented here, you would have this molecular species, which you would then weigh, and you would also have this molecular species, which you would then weigh. So you're going to get two fragments here. Some other times it'll fragment here, and you'll get one smaller fragment, one larger fragment, and you'll weigh those pieces. And if we do fragment the peptide enough times, we'll fragment at each of these peptide bonds. We'll get measurements of all the different fragments that can occur. And then we'll see how that leads to an identification of the peptide. Now, last thing I need to say here is that when you fragment this, you have, again, this is the amino end because the amino end is free. Here's the carboxy end. Whenever you fragment a peptide, this ion, the one that's on the carboxy side, is going to be called the Y ion, and the one that's on the amino end is going to be called the B ion. So let me erase this slide, and then I will continue. Okay, so that's cleaned up. And just to see these ions, here's the first amino acid, here's the second amino acid, therefore this is the B2 ion. Here's a third amino acid, here's a fourth amino acid, so then this would be the B4 ion. Here we're going to count amino acids from the carboxy end. Here's one amino acid, here's two amino acids, here's three amino acids, therefore this would be the Y3 ion. Now occasionally you're not going to fragment always on the peptide bond, even though that's predominant. Sometimes you might fragment between the alpha carbon and the carboxy group. This would be called an A ion then, and if you fragment between the amino group and the alpha carbon, that would be a C ion. Likewise, so here are the three amino acids. We have the Y1, Y2, Y3 ion. If we fragment here between the alpha carbon and the amino group, we'll have a Z ion. If we fragment between the carboxy group and an alpha carbon, we would have an X ion. So we have XYZ ions, ABC ions, and that's the reason for the title of the article that you're reading, the ABCs and XYZs of mass spectrometry. So, and this is going to show what data will start to look like. We have this peptide with a number of amino acids. We're going to fragment it at as many places as we can. These small fragments like the B2 ion and the Y2 ion, those will be only two amino acids. Those will be pretty small. Maybe this is B2, maybe this is Y2. And then we're going to have larger and larger fragments. Here's a Y7 ion. This is right here. This would be one of the largest peaks that would be observed. But by fragmenting it all, we're going to generate lots of different fragments, both the B and Y ion series, and then we're going to use this pattern to calculate its identity. Okay, so now we've set the stage for data acquisition. We'll go through the details in the next video. Thanks for listening.